सर प्रणाम सर।
नमस्कार नमस्कार
नमस्कार नमस्कार सर।
कितने अच्छा अभी आ गए ना काफी लोग आई थिंक।
जी सर जी। गुड मॉर्निंग सर।
51 लोग। हाँ गुड मॉर्निंग गुड मॉर्निंग। सचिन कुमार, डॉक्टर अशोक कुमार बाघा।
गुड मॉर्निंग सर।
गुड मॉर्निंग प्रमोद कुमार जी।
बढ़िया सर।
गुड मॉर्निंग सर।
ठीक है ना। अच्छा जी ओके बोलो। अर्जुन सिक्का। ये आपका स्पॉन्सर प्रोग्राम है ना?
जी सर जी सर।
कहाँ से? आईसीटी का?
नहीं सर, मतलब जो रजिस्ट्रेशन फी है उसी से ही।
उसी से आप सेल्फ? अच्छा आप सेल्फ
स्पॉन्सर्ड
सेल्फ फाइनेंस्ड कोर्स। ठीक है अच्छा है। तो पार्टिसिपेंट सभी जगह के हैं है ना?
जी सर जी सर जी सर।
ठीक है अच्छा है। गुड। तरुणप्रीत सिंह।
दीक्षित सर नमस्कार।
नमस्कार नमस्कार शुक्ला जी नमस्कार।
कैसे हैं सर?
मैं ठीक हूँ एकदम ठीक हूँ। और आप कैमरा ऑन करिए तो आपका दीदार करता हूँ।
बहुत दिन बाद आपके दर्शन हो गए हैं सर।
नहीं आपके गाइड से तो मेरी बात होती रहती है पांडे जी से।
सर प्रणाम सर। प्रोफेसर विनोद कुमार कौरजिया सर है ज्वाइन।
अच्छा नमस्कार।
नमस्ते सर।
नमस्ते नमस्ते
सर मैं रुचिर जी का फ्रेंड हूँ।
अरे अच्छा अच्छा।
मैं कल डिस्कस ही कर रहा था कि मैं रुचिर जी का और डंडपा सर के साथ में काम कर चुका हूँ सर, प्रोफेसर समृद्ध डंडपा।
अच्छा अच्छा आप गुवाहाटी आए थे कभी? आईआईटी गुवाहाटी?
नहीं गुवाहाटी नहीं, मैं बरेली में था साथ में।
अच्छा तब आप अच्छा वो भी थे कुछ दिन उन्होंने काम किया था।
हाँ कुछ दिन उधर थे।
वहाँ एक प्रोफेसर एम अग्रवाल भी थे, आपको शायद याद होगा बहुत पहले जिस मैकेनिकल में। हाँ ये मेरे बीटेक के सुपरवाइजर थे वो।
अच्छा अच्छा।
बीटेक में
तो रुचिर से बात हो रही थी, हमने कही सर से वर्चुअल मुलाकात होगी, अब फिजिकल बाद में होगी।
हाँ ठीक है बहुत नहीं आपका होम टाउन मेरे घर के पास ही है ना? आप कहाँ के?
हाँ सर पास में ही है सर।
कहाँ के हैं आप? होम टाउन
इटावा का हूँ।
इटावा के ठीक है। तो मैं कानपुर
उन्नाव के पास के।
उन्नाव है।
हाँ मालूम है मुझे सर, उन्नाव का मालूम है मुझे।
हाँ ठीक है ओके गुड। चलिए बहुत अच्छा।
So let's start the ceremony. Jitendra please.
The sparkle of fire is the witness of your worth. The silent fluence of water is the witness of your softness. The rising of the sun in the east and the sunset in the west is the witness of your rhythm. Rhythmical movement of the moon is the witness of your perfection. A word, a soul are the witness of oneness of glory, whose glorification cannot be described in words. A warm good morning to Honorable Director Sir of NIT Jalandhar, Professor Vinod Kumar Kanudia Sir, respected Deans, Head of the Mechanical Department Dr. Pramod Kumar Sir, Course Coordinator Dr. Manoj Kumar Sir and Dr. Ashok Kumar Sir, and all the faculty members, researchers, colleagues and dear participants. With the core of motivation, I, Jiten Basrani, research scholar, feel privileged to welcome on the behalf of Dr. B.R. Ambedkar, National Institute of Technology, Jalandhar, to the inaugural ceremony of the 5 days faculty development program on FEM and model analysis in engineering. This course is the need of the current time as we get the opportunity to increase our knowledge and understanding. This FDP is the result of the efforts of Head of the Department Dr. Pramod Kumar Sir and Course Coordinator Dr. Manoj Kumar Sir and Dr. Ashok Kumar Sir. Dr. Pramod Kumar sir has done his PhD from NIT Jalandhar and his research areas are renewable energy and FEM analysis of composite material. Dr. Manoj Kumar sir is the faculty in Mechanical Engineering Department, has done his PhD from IIT Kanpur and his research areas are continuum damage mechanics model, dynamic fracture mechanics, high strain behavior, finite element method, computer-aided design. Dr. Ashok Kumar sir is also the faculty in Mechanical Engineering Department. He has done his PhD from IIT Delhi and postdoctorate from NTU Singapore. His current research areas are characterization and model analysis of microwave welded metallic joint and finite element model, updating of composite and smart structure. I would like to call Dr. Manoj Kumar sir to elaborate the course detail. Over to you, sir.
Yeah, thank you, Jitendra. And good morning to all of you. And Professor B.K. Kanodia sir, our director sir, I warm welcome you to in this STC. Professor U.S. Dixit sir, the chief guest of this FDP. Professor Pramod Kumar sir, head of department. Dr. Ashok Kumar sir, coordinator of this course, and my dear colleagues. And warm welcome to our all of participants from different institutions and different places from this country, including IITs, NITs, PAC, DCE, and different institutions and different places of these countries, including I can say that from Kerala, from MP, from Delhi, Gujarat, and Punjab. On the behalf of organizing committee, I welcome all of you in this FDP. This FDP on finite element method and modal analysis. Here you will learn about finite element method. We all know that nowadays finite element method is the emerging field, and everywhere we are looking and implementing this method to analyze the structure problem. As well as nowadays people are using dynamic problem also using FEM. And if you see that a simple dynamic problem, if I say that automobile problem, where we will be looking of modal analysis using FEM. We will see all these in this conference. Today lecture will be delivered by Professor U.S. Dixit sir, and tomorrow will be given by Professor Sachin Singh Gautam sir from IIT Guwahati, and day after tomorrow Professor Puneet Mahajan sir, and then we will be looking Professor Modek sir from IIT Delhi, who will be telling about modal analysis. And now I thanks to our worthy director sir for giving me this opportunity to conduct this STC on this emerging field, and thanks to our head of department and our all colleagues to supporting me to conduct this course. Thanks. Okay, Jitendra, please.
Thanks, Dr. Manoj sir, for briefing about the course. Now, I would like to invite Dr. Pramod Kumar sir to address the Mechanical Engineering Department.
Good morning to all. Respected Director Sir, Professor Vinod Kumar Kanodia, and Professor U.S. Dixit. I welcome all to this short-term course, and I would like to talk about my department. As HOD, it is my responsibility that I should inform about the department. This course, Finite Element, is organized earlier also by Dr. Manoj and Dr. Ashok. They all are very much interested in finite element analysis. In our department, we have different facilities. Many computational computers are there, and software like Abacus and ANSYS we have. And other than this finite element analysis, we work on the material. We work on the heat transfer. Many equipments are there for testing the materials, like universal testing machine. This is one of the most important and only available in this zone in our department. We have the testing facilities of the model analysis related to model analysis carried out by Dr. Ashok, and the heat transfer. Other than this heat transfer, we have a very expertise person in our department like Dr. Subhash Chandra, and in one of the another field which I would like to talk about, the megatronics, which we have the expertise in our department. Professor Anand Bas is here. If any work comes, then we can carry it out. And other than these facilities, we have the solar working group here. Many faculties are working in the solar energy, including me, and biorenewable energy also. So, lot of things we have, and we are interested in doing the project work. We have Dr. Srinivas, who is doing a lot of work in our solar energy. And new faculties are also, they works a lot in this field. So this way, this is our department. We have very sincere faculty in our department. Any work we can do. Therefore, I request any participants, if they want to talk to any faculty, they are most welcome. And in the field of finite element, we have the expertise in this field also. Dr. Manoj is one of our experts. Myself also works in the finite element. And Dr. Ashok, who is the course coordinator, he also works in this field. And any type of problem we can analyze, including the composite analysis, fracture analysis, all these things we can do in the department. That is our strength of our department. That's all. I think over to Jitendra Basrani to carry it out.
Thanks, Dr. Pramod sir, for briefing about the mechanical department. Now I would like to call again Dr. Manoj Kumar sir to address the worthy director sir.
Yeah, I welcome to our worthy director sir, Professor Vinod Kumar Kanojia sir. Professor Kanojia sir joined NIT Jalandhar as a director on 5th February this year, 2020. Prior to this institution, he was a full-time professor at JNU. He was a professor in the Department of Electronics and Communication Engineering in Ambedkar Institute of Advanced Communication Technology and Research. Formerly, this institution known as Ambedkar Institute of Technology, Delhi. He also served here as a head of department from 2008 to 2010, and then 2012 to 2014 in the same institution. Before this institution, he joined as a faculty member in MJP Rohilkhand University, Bareilly, UP, as a lecturer in the Department of Electronics and Communication Engineering. He also served here as a head of department from 2006 to 2008. Professor Kanojia sir did BTech from KNIT Sultanpur in 1994. And after that, he did MTech and PhD from IIT BHU in 1998 and 2004 respectively. Professor Vinodya sir has published more than 350 research articles with more than 4,300 citations of his research work. He wrote several research, that means book, and textbook also. His main research area and specialization are modeling of radio frequency design, dielectric resonator antenna, mobile communication, computational radio frequency radiator. Thank you, Professor Kanodia, sir. And we are sure in his guidance, this institution will achieve new height. Welcome to Professor Kanodia, sir. Sir, please.
Okay, thank you, Dr. Manoj, and good morning to everyone. So, greeting from NIT Jalandhar, special to greeting Professor U.S. Dikshit, sir. So, we expect that from Dr. Pramod Kumar ji, Head of Department from Mechanical Engineering. So, we invite Professor U.S. Dikshit in physical, sir. So, that is my pleasure for NIT Jalandhar. So, Professor U.S. Dikshit from IIT Guwahati and Professor Pramod Kumar, HOD Mechanical Engineering, and coordinator of a course, Dr. Manoj Kumar and Dr. Ashok Kumar, and Dean and faculty member and other participants and registrar, Dr. S.K. Misra is also there. So good morning to everyone. So it is my privilege to be part of an inaugural function of a faculty development program, or we can say that a short-term program on a finite element method and modeling of analysis in engineering. And that has been organized by Department of Mechanical Engineering, NIT Jalandhar. So we expect from this course in a finite element method, we have worked on one of a tool that for a electromagnetic that is based on a finite element method. Even that in some of a popular technique is FDTD and finite differential time domain. So that is very important for a different discipline. So if the researcher, they will work on a different technique, or we have some of a possibility, we will work on a different technique. If we design of any new technique or some new algorithm, or some of a, we propose of some of a technique, if we compare of a different technique and taking of a result of any that structure or some of a system, then we propose of some of our algorithm or some of a method. I think that should be a more contribute. So if we work on a finite element method, so this is one of a tool. So researcher can learn that how we will go towards of a designing of a tool for a different application. And the concept is same, but in a which type of a boundary condition we have considered and which type of a application we have considered. So in a using of this boundary condition and some of a system, we can propose of some of a technique. So that should be very useful for our country or for our researcher. So we will focus on to go in a detail to how this technique is solve the problem. So you can understood that how you can propose some of a techniques that can be useful in a future application. So the finite element method is most powerful method for analysis of an engineering problem. So it is a process of simulating and behavior of a part of a mechanical system, civils and aerospace structure, and nowadays finite element method is a field of a nanotechnology in a continuously contributing to the area of a ranging from electronics, microcomputing, and material science and quantum science and biotechnology and medicine and computational nanotechnology. So in our country, some of our researcher and some of that scientists, they are doing very well in a case of a computational work. So we will take the privilege and we will focus on these type of technique in a basic core field. So it is my privilege from a NIT Jalandhar, one of a national institute, or we can say that one of a national accolades and outstanding institute of a higher learning. NIT Jalandhar is ranked 49th of a National Institute of Ranking Framework, NIRF, and band excellent in a Atal ranking of institutions on innovation and achievement, and was recently ranked in a 4001, 2 and 500 range in the Times Higher Education in Emerging Economy University Ranking 2022. These accomplishments are result of our dedicated faculty members, staff, and considerable effort by student. So we welcome Professor U.S. Dikshit and we request Dr. Pramod Kumar. So we invite Professor U.S. Dikshit. So we will take the expert some in a different field. So once again, I congratulate to Department of Mechanical Engineering for organizing this FDP or STP for a finite element method and modal analysis of engineering. Jai Hind, Jai Bharat.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir, for your influencing message. We are charmed by soft influence. It was indeed a great experience hearing from such dignity. Now, I would like to call Dr. Manoj Kumar, sir, to welcome and introduce the experts of this FDP course.
Yeah, it is our privilege to have Professor U.S. Dikshit in the inaugural ceremony. Our sincere thanks to Professor Dikshit, sir, to accept our invitation for the expert talk on FEM. Professor Dikshit, sir, is a full-time professor in IIT Guwahati from 2007. He joined IIT Guwahati in 1998. He did BTech from IIT Roorkee in 1987. Then after he joined HMT. And after HMT, he joined MTech and MTech at IIT Kanpur in 1993, and then he did PhD from IIT Kanpur in 1997. Professor Dikshit have published more than 150 research articles with citation around 2,500. He has written almost 15 research books and textbook, around 30 book chapters. He has completed more than 90 research projects and consultancy, which are from several funding institutions like DST, MHRD, AICTE, etc. His book on finite element methods for engineers is very liking among all the students and faculty members. I welcome to Professor Dikshit, sir. Please, sir.
So at the outset, let me congratulate the director, Professor Vinod Kumar Kanojia ji, and I wish all the best under his tenure. This institute should achieve greater heights. I have been coming to NIT Jalandhar once upon a time. In fact, I was coming 4 times in a year actually, maybe even more. Particularly, I used to come in the production engineering department. And I have seen that before Professor Avasthi was there, director, that time also institute progressed a lot. And I am sure that under the leadership of Professor Kanojia, the institute will achieve even greater height. Maybe that IRF rank will be within 25 actually. That is what my expectation and my good wish for this one. Okay, so now it is indeed now FEM as a subject has become very important for everybody. So there are 2 types of people that who need FEM, okay, who has to study FEM. One is that those people who will be applying it for various applications. Nowadays, it becomes in fact difficult to avoid FEM, even if you are doing completely experimental work. But people want that you should justify it by FEM, you validate it. What is this one? Even in the structure, earlier days we made many buildings, but of course that time FEM was not there. Nowadays, if you make a building, then the customer will insist that where is the analysis, strength analysis, and that means you have used FEM. So in structural analysis, it has become mandatory. Even if you are doing something, you are developing metal matrix composite, studying its property. But if you substitute it, supplement it with FEM analysis, then the chances of publication in a very reputed journal will increase. So as a user, everybody should know. So nowadays there are many packages like ANSYS, Abacus, Elasticity, many packages are there which can be used, and it is not difficult to learn. because all the things are there. But it is essential, therefore it has become essential that you should know some basics of FEM, why it is happening. It is not a magic box. So one should know the limitations, one should know what is going on. So that is one thing, that's why that FEM is important. Other thing is that, as Professor Kanojia was also pointing out, that there are different problems in which, you know, that maybe that application of FEM has not been explored. Maybe we have to modify some technique. Maybe we have to write our own code. For that purpose also FEM is needed. So in fact, I will be giving my address. I think that after this function, inaugural function, because director sir is busy, I think you will give me 1 hour time. Is it not, Dr. Manoj?
Right.
That I show with the PPT, but at the outset only I want to tell to the participants that this course is important for everyone, even because FEM is basically, in one sentence, it is a method of solving differential equations, and they may be time dependent also. So FEM borrows the techniques from other areas like FEM and FDM combined, where you know that a spatial problem is solved by FEM and time part is actually solved with the help of FDM. So by combining this thing, so it requires, it is basically a differential equation. Therefore, it can find application in any field, even in humanities and social sciences also. If you can identify that this is the differential equation, then we can do. Many management people are nowadays using, they are modeling, doing system dynamics. So that is why this course is very important, and I congratulate both the organizers to have this type of course in the self-sustaining mode. It is heartening to see that the people have come by paying the registration fee. That means they will show more sincerity, and that itself shows that they have desire to learn. Because many times what happens, if you get from some sponsoring agency, then participants do not take interest. They think that, okay, it is like that and I have to get a certificate. But here you have a strong desire to learn the subject, and our Dr. Manoj Kumar and Dr. Baghaji is also very proactively have been organizing such type of courses. So with these words, Dr. Pramod Kumar is naturally in touch with me, and we have also met many times. So again, I am very happy to note that actually our director Vinod Kanojia ji has come, although we have not met him, but you know what, his simple personality, you know that his way of talking, you know, and connections, like he said that he knows my friend, the Professor Ruchir Gupta also, even Dhanpat ji. So we all are connected. And not only that, you know, that I know about even that institute also, KNIT Sultanpur, from where he has done BTech. These are, you know, because I hail from the UP only, and therefore although most of my working life has been outside, particularly major part of my life was spent in Assam, but naturally one has the attachment. अपने मायके का मोह जो है सबको होता है, so that my मायका is basically in this one, Unnao, Kanpur, Itawa, and all these things. So naturally, and Jalandhar people are also very close to me because I keep coming, and whenever I come to Jalandhar, I also go to Amritsar. Always they arrange my trip to Amritsar, वहाँ मत्था टेकता हूँ, तो then I feel this one. So it is very good that we are getting that a director who is just like अपने घर का आदमी जैसा feeling हो रही है. We have that this one, he's so simple, and this one so naturally, without fear, without any type of problem, without any type of any hassle of bureaucracy, you can now work. Because if you get a leader who is very motivating and who delegates the power, then naturally the employees will be successful and they will reach greater heights. So with all these words, I stop my
yes,
Jai Bharat, Jai.
Thank you, sir. Thank you, Professor Kanojia, sir, and thank you, Dr. Pramod, sir, Dr. Baga, sir. And now we will be having a session on fundamental of FEM, which will be taken by Professor Dixit, sir.
So I can share my PPT now.
Yes, sir. Please. Okay, please. Sir.
Yeah.
Okay, sir.
Yes.
And I request to all the participants, whenever you face problem, you can immediately WhatsApp me. And I will convey the your problem immediately to Professor Dixit sir.
Yes, yes.
And even I will try my best to solve your problem.
In between also you can, stop me.
Yes, sir. Yes.
Okay.
Manoj sir, Dr. Manoj. Participants, I have also one request to you. Please, this FDP should be an active FDP. Please ask questions. If you have any doubt, you can ask question to Professor U.S. Dixit sir. Because most of the time when we study the FEM, so we forgot to learn about the basics and other things. So I just request to all the participants, this PPT, this FDP should be active. FDP, not a passive FDP.
Interaction. I should say the interaction. Totally
interaction is very important. So at any stage, if you have any doubt, you can ask question to sir, and it will be very good for you. You can apply those things in your future learnings, and you can learn new things also.
Yeah. Okay. So let me give a very simple introduction. Most of the people get frightened by finite element method, but today I am going to give an introduction which I think all of you will easily grasp. And this type of thing is not available in any book, not even in my book actually. That means it is so different way I am trying to present the things, because many people have some misconception, because finite element method can be used for solving a variety of problems. So, and it solves the complex problem. So people think it is a complex thing, but actually its philosophy is very simple. Now detailing may be complex. Okay. So what is a FEM? So first, suppose somebody says that just tell me in one sentence, then we should say it is a numerical method for solving differential or even integral equations. So basically it is a method of solving equations. I can say differential equation, or I can say even algebraic equation, because in a way, algebraic equation is also a zero order differential equation. So for knowing how it works, let us take a simple example. Now, example is that I have deliberately chosen a very simple example, that this differential equation, suppose it has been given to you. Differential equation is d square u by dx square plus 5 equal to 0. And at x is equal to 0, u is equal to 0. At x is equal to 1, du by dx equal to 0. So these two boundary conditions have been given. This is a second order differential equation. If I ask you what is the solution of this, you can easily tell me. It is very easy in this case, because you just say d square u by dx square equal to minus 5, and then you integrate it 2 times, double integration, you get back the value of u, but because of the integration 2 times, you will get 2 constants of integrations also. So those constants will be found by applying these 2 boundary conditions. That's why you need 2 boundary conditions, because with one boundary condition, you cannot solve that. So it is very easy that you can always say that, okay, this is the boundary, this one, and you will say that, well, the solution is u is equal to 5x minus 2.5x square. You will give me the solution, is it not? Because you just integrate. First time I integrated, I got minus 5x. Next time I integrated, minus 5x plus constant. Then I integrated, I got minus 2.5x square plus ax plus b, like that. And then you put the boundary condition and do that, and you give this one. Now, for a while you think, let us say that I am your teacher and you are my students, okay? And everyone is my student, and I just want to judge you. So I give this problem, I just noted this one and I just give. And you give me the solution. But let us say I myself do not know. I am, that very weak teacher, or maybe not weak, but maybe absent-minded. I do not know I forgot that how to integrate. But as a teacher, I have to check what you have given to me. U is equal to 5x minus 2.5x square. whether you are right or not, because I have to give marks on that basis. So how do I do that? Now, you have done by systematic procedure by integrating, but I have not done that. I do not know the integration. So what I do that? Is it means whatever that, let us say Baghaji has given me solution, whether the Baghaji is correct or not. So I say, okay, Baghaji, your solution is this. Let me put the boundary condition. I said, okay, at x is equal to 0. Acha, this is becoming 0. So I am happy. And then I say, what is du by dx? I say minus 5. Okay, minus 5 x and minus and plus 5. Okay, 5 minus 5. And I put x is equal to 1 and say that it is satisfied. So I say, okay, Baghaji, aapka boundary condition to satisfied hai. It is good. You have satisfied the boundary condition. Then let me see that your differential equation. What I will do that? I differentiate it 2 times. Okay, I differentiate it 2 times, and then I got minus 5, and minus 5 plus 5 equal to 0. So I say, okay, your boundary differential equation is also satisfied. So that means it is very correct that this is a solution. So I say, okay, Baghaji, you will get 10 out of 10 because you have given me the solution. Now the question is that if a computer has to do in place of me, suppose there is a computer, okay, and he has to check the solution, probably the computer also can check in that way. But now think the reverse problem. Suppose the computer has to solve the equation like that. So computer does not know proper integration, although there are some software, they do some integration also nowadays. But let us say this problem is only simple. In a very complicated differential equation, how it will solve that computer? It is very difficult that computer knows that how it is solved. There are many techniques. So, but I am telling another way, like I have done. One way is that a computer keeps substituting a number of functions in the equation. The function which satisfies the differential equation and boundary condition is the correct solution. Can there be one type of this type of method that I don't have to teach any algorithm, much complicated algorithm to computer? My task becomes very simple. What a computer is there, let it assume number of functions, okay? Number of functions it should assume, and it should try to fit in this one which satisfies the equation and boundary condition. That becomes the correct solution. Can a computer do that type of things? So this idea looks very simple, because instead of asking me to, that learn the methods for solving the equations, etc., this is much easier approach that if we just pick up. Is it not? You see that our early forefathers also many times they used to solve that complicated problem, that they asked the children some puzzle. This is the thing that, this type of thing that, say many type of interesting puzzles that suppose at somebody's house that some people have gone and he has number of carts, but if he gives one cart to sleep to one guest, then one cart will be short. There is a shortage of one cart. And if you know that he does the otherwise, that 2 persons share one cart, then one cart will be unused. So what is this one? So children ask this type of thing. Ki chalo bhai 4 karte hain. Suppose there are 4 carts and 3 guests. No, it doesn't fit. But 3 carts and 4 guests it fits. So can a computer do that type of things? I am just giving this type of introduction to you to motivate, so that some of you can try to develop the innovative methods also. So this idea is fantastic, that if a computer can check lots of functions, but only problem is that there are infinite number of possible functions. So how much time it will take? It will be checking. There is no end to it. It is not that functions are finite, that there are 100 functions and you check that. That can be useful if somebody tells that, okay, there are these 100 solutions, pick up one. That is okay. So, but somehow, suppose we know that the desired solution is quadratic. Suppose already we have observed the experimental data and all those type of things, and we know that it is going to be quadratic. Or in the fractal mechanics problem, when there is a crack, we already know that at the crack tip it will be very, very high, almost infinity, and other place it will exponentially decay or something. That means we have some idea. Then it may be easy for a computer to find out the coefficients of the quadratic polynomial or whatever polynomial or any function we set which provides the least error. So then our job becomes somewhat simple, that you don't have to find out infinite number of things, but you have to pick up only the coefficients which they satisfy. But how do we know the form of a solution? That is one question. And so the question is, so that is why, so if we do that, so there is one thing, if we limit our domain to a small size, we can easily approximate the solution to a low order polynomial. Okay, so that is what the basis of finite element. That means you divide and conquer, make a small domain or something. If we just talk about this thing, that this is the function and it can be anything and it may be very complicated, then even computer will fail to do that. But if the computer is told that you know that in this particular domain it is just linear variation, then it can solve. So how the computer will know that it is just a linear variation or something? If we just limit, sometimes I give students this example that see, our earth is spherical, right? It is a sphere. So I say that, okay, suppose this is a football, and in that you just stand. Can you stand? Can you do? No, you are falling. You are not having. So then how we are making the houses? They think that what weight question he is asking, that you know that earth is spherical. So I said earth is not flat. So then they said, some smart guys, they said, no sir, what you are talking, earth is spherical, but in this small area it looks flat. So I said essentially the same thing. You know that actual curve, you know, like temperature, suppose it is variation of yield strength of a material with temperature. Now actual variation is shown by the experimental, some dotted one. It is, you know, very this type of thing, wave type of thing. It's not a straight line. But I can try to fit piecewise linear fitting. I can say from here to here it is a straight line, from here to here it is a straight line, from here to here it is a straight line. And then a straight line is characterized by 2 points. If you give me the coordinate of 2 points, first point and the last point, I can fit a straight line. So I have this one, this one, this one, this one. So if I have a solution in the form of the dotted line, I can say that my problem becomes only just to find out these quantities. That means at different temperatures, at 4 temperatures, I should know Y0, Y1, Y2, Y3. So it is like that. So Y0, Y1, Y2, Y3, that much only I have to find. So my problem got a bit simplified. Why? Because I took the small element, and each element I assume that it is a linear fitting. Okay, so then I can find, but not that I am getting the value at only these points in the solution. My computer or that calculator, it will give the values at 4 nodes. We call these nodes. But you in between, you can find out any value by joining the straight line. So that means this is why in FEM we discretize a large domain into a number of small elements. That is why it is called finite element method, because each element is of a finite size, and in each element I can approximate the solution by a low order polynomial. Even if it is a higher order, even if it is a complicated, in a small domain it will look like a simple one, like here a straight line. It is looking a straight line from here to here. Although you can even, if you want, you can fit even quadratic also. You can say quadratic, you can find fit a trigonometric, any function you can fit, but you can actually, and straight line of course is the most simple one. So straight line also can be fitted, and in fact most of the applications just fit the straight line, but higher degree polynomials are also fitted. So that is one thing, that it is because of that this is finite element. So then with this, let me expand the definition, which I just said in, that only a few sentences. Now I am telling a little bit more difficult, because otherwise the person who is interviewing you will not be happy. He asked you FEM and you answered it is a numerical method for solving differential or integral equation. Then he said, okay, that any means even FDM also does that. Then what is the finite difference also does that. So what is this one? Even Simpson, this one, Rangai-Kupte also does that. So what happens? So let us expand the definition with this background. So FEM is a numerical method of solving differential or integral equations in which the domain is discretized into a number of small elements. That means we have to discretize into number of small elements, and in each element a simple form of the solution function is assumed, and attempt is made to find out the parameters of the function by minimizing the error of the solution. So that is this one. If you understand this definition very carefully, then you will understand the difference between finite difference method and finite element method. Many people are not clear about that difference. Finite difference is what? Finite difference is just what we have studied in class 12. In fact, before differential calculus came, such problems used to be solved only by finite difference. Finite difference means this. Suppose you say that what is velocity? Nowadays you will say what is the relation between velocity and displacement. Now if I ask any student of maybe class 12, he will say that, sir, velocity is equal to, I say, tell me mathematically, then he will say V is equal to ds by dt, isn't it? He will say V is equal to ds by dt. That means it is the derivative of displacement field. Okay, you get a velocity field. That is what is this one. But what is that ds by dt? So actually ds by dt is basically s at one point, then s at adjacent point, something like s2, suppose s2 minus s1, or s at time t plus delta minus st divided by delta t. That is this one. That's how you will calculate. That's how that a common man will calculate the velocity. Is it not? That, suppose you ask the velocity, how much is the velocity? I myself do something like that. Suppose I am sitting in a car and I just go and I see that 1 milestone, that means kilometer stone. So I say that, okay, it is 56. That destination is 56. After that, it has become 55. So I see my watch that in 5 minutes we have moved only say 1 kilometer. So that means my speed is 12 kilometers per hour. Like that, people do that. Suppose I am moving a cycle also, I'll do this type of thing. So finite difference is basically going back to that old technique. That means you have differential equation, but you change into difference equation. That means what we teach in the calculus, that we say that they derive the derivative from the first principle. First principle means if I want to find out derivative of sine x, I have to do sine x plus h minus sine x divided by delta h, limit delta h tends to 0. So forget about limit part, just divide it delta h and say that this is my solution of this one, differential. But of course delta h should be small also. We cannot make it 0, we cannot tend it to 0, but we make it very small. That is called finite difference. So philosophically it is totally different, because it is nothing but you are converting the differential equations into algebraic form by using finite difference. Okay, say different derivative means difference between two quantities divided by another quantity, that means time interval or what, that is what is the finite difference. But finite element is a different thing, as I have told that. It is that here we assume some function. So in the finite difference, always there will be something like yx plus h minus yx divided by h, and it looks like a that linear type of function. But here you can choose anything. If I know that my actual variation is exponential, I can use exponential function. And I can use, if it is trigonometric, I can use trigonometric function. So then the question is that this is the method actually. But then why do we find out solution in the form of nodal values? Because many teachers and most of the people, they will say, okay, they will make the element, they will make a diagram, they will show small elements, then they will show nodes. So the question I want to say actually, nodal value. Am I audible? Any problem? Am I audible? Yes, fine. Okay. Very good. Okay. So I'll just move ahead. Okay. Now here, yeah. Okay. So in this case, so question becomes like this, that actually nodal, why do we find nodal values? Because when I am telling that find out the parameter of the function which has been fitting, so nodal values act as the parameter of the function. This point also has to understand. Like I am giving the example, I told already in my previous slides that you know that I can have, suppose temperature distribution. Many of the mechanical engineering department people, they, as Pramod ji said, that they are doing heat transfer. So in heat transfer, suppose you have got a temperature field. Now that temperature field is very complicated. But then what do you do that? You can make it, you can assume that in a small domain, it is linear. Let us say that you are solving 1D problem. Even in 1D problem, the temperature distribution may be very complicated. But you assume that in a small element, it is T is equal to A plus Bx. And then for each element, you find out that value of A and B. And if you have done, this is FEM. But then you may say that, okay, some of you have got exposed to, sir, no, this is not FEM. We don't find out A and B. We find out the nodal values at this one endpoints. We find out T1, T2. My software only gives T1, T2, the values at the node. So I want to say that, okay, open your mind. It is actually you are finding A, B basically. Not that this one, because what T1, T2 at two locations, that can be expressed in terms of A and B. So that is what that you are basically doing. That means you are not doing any finite difference thing. It's not that you are finding out the values at the nodes. You are finding out the complete function. So therefore, you can also add some constant which doesn't have any physical meaning also. It may not be nodal values. Nowadays, we do P refinement. Nowadays, those type of things that we just add something which doesn't have any physical meaning. Nodal temperatures have physical meaning that at this node, this is the temperature. But you can add something, some incompatible mode. So in future, you may get that type of situation. So that's why I wanted to widen up that thing, that don't think that you are only doing nodal values. You are finding out the complete function in that small domain. And then with that function, you can find out value at any place. So in general, what is the finite element methodology with this now? What it does? First step is pre-processing, okay? That in finite element packages also pre-processors are there. Here you make a geometry. That geometry is discretized into number of small elements, and that is called mesh generation. Mesh generation itself sometimes may be very important activity, and many people in the area of computer graphics, they work on the mesh generation. Automatically it should generate the mesh or something. Otherwise, manually also you can make, you have domain, you discretize it. Whether you make if it is a 2D problem, you can have number of triangles, you can have a rectangular one, you can have this one. So this is what that pre-processing, and then you can do material property, etc. So before doing the FEM, you can make this preparation. Then what you have to do? For each element, because we discretize it into number of elements, so for each element, algebraic equations are found for each element. That can be done by various methods. even direct FEM formulation, that means based on the physics also you can discretize, but there are other methods also, little bit we'll touch upon that, okay. So this part, that how to make computing, how to make elemental equations based on the differential equation, this part requires little bit skill, okay. That is what we have to study, and this is the core part of the FEM. But in the packages you will not get this type of thing. You will not even see that what equations it has, because for standard problems only they have made the solutions, and they keep taking that. So analysis part is embedded into that. So unless you are designing your own software, probably you will not know that, but you will using that package, okay. Then assembly, these elemental equations, suppose there are 100 elements, but then you have to join and you have to make one complete problem. So that means you assemble that and you get a global system of equations, and then you apply the boundary conditions. That assembled system of equations is modified by inserting boundary conditions, okay. And then you obtain the solution. That means those equations, most of the time, those equations will be only the linear equations. Even if they are non-linear, you can also, by numerical method, in some way you have to solve the linear equations, and then you have to use Gauss elimination method or whatever, and you get that type of things. So you get a solution. Like solution means my differential equation is something displacement. So I get displacement at each and every node. But then there is a lot of post-processing work. That data you have taken, then you can plot contours, you can do many things. You can find out the derivative quantities like stress, strain, so many things you can do. That means this part is called post-processing. So packages will have preprocessor, they have processor, they combine all these steps, they call processor, and then you have post-processor. So now the question is that how the package does, or how FEM works, that I am just explaining in a very simple toy type of problem. But if you listen it very carefully, then you know your problems will be solved. You will understand, okay, this is the thing which I can learn and I can do that. What is that problem? It is a direct sum FEM formulation of axial rod problem. This is a axial rod. I am opening by stretching it by applying a load P. So in this case, what happens that my deflection becomes PL by AE. A is the uniform cross section. So it is obvious problem, but let us try to do it by FEM. Let us say I don't know that deflection is PL by AE. So how should, and maybe I have taken very simple, but you can have tapered rod and something. Maybe you can do for this problem, but for tapered rod you will face difficulty. And if the material properties are changing from point to point, then also you will face difficulty. But in FEM, for each material, suppose up to first half it is brass and up to second half it is steel, then you can make two elements and say that here I put the property of brass, here I put the property of steel. So there are advantages. But for explaining purpose, I should take a very simple example so that you can keep understanding. So first step is pre-processing. So whatever that rod was given to me, I just divided it into 3 elements. So this is 1, 2, 3, and these are the nodes 1, 2, 3, 4. Then I want to make the elemental equation. So I choose a typical element, and then what I do that here this is Fi, this is Fj, and this is node I, this is node j, and then I for each element I write some equations based on our understanding. Say strain epsilon t, tensile strain is uj minus ui by h, because suppose it got stressed by j, uj, and this is ui. So uj minus ui is the relative stretching, and divided by h, then stress becomes just multiplied by E, then force becomes multiplied by area. So that means AE uj minus ui by h is equal to Fg. This has come from our basic understanding that this is AE uj minus ui by h. And if I focus my attention towards this node, ith node, and if I say that I is getting compressed then I can say compressive strain is Ui minus Uj divided by H, and stress is equal to sigma C is equal to E into Ui minus Uj by H, and force is equal to AE Ui minus Uj by H is equal to minus Fi. So that means that this becomes minus Fi because I have chosen the direction of Fi in this direction. So that's why it has become minus. So I got these two equations. No doubt these equations will be correct because AE Uj minus Ui by H will be Fj, and AE Ui minus Uj H is equal to minus Fi. Maybe some of you who have studied mechanics may immediately ask that question, that sir, that Fi will be equal to Fj, is it not? So I say that okay, fine, it will be equal, but I am just writing it that way. But of course it will be equal. Don't worry about that. And it is showing equations are also showing that AE Uj minus Ui by H, and this is nothing but the negative of that Ui minus Uj by H. So of course they will be equal, but time being allow me to write in the general way. So this is AI by H, 1 minus 1 minus 1 1 Ui Uj is equal to minus Fi by Fj. So what I have done, that I just have written these two equations in the form of a matrix, because after all, what is the major use of a matrix algebra? Why we study matrix? Because I can express my equations in the matrix form. So whole thing, so basically what you are seeing is nothing but these are the two equations. So we say Ke Ue equal to Fe. We just say this coefficient matrix as Ke, and this we say as Ue, and this is Fe. And with analogy of spring mass system, I say Kx is equal to F. So K becomes stiffness matrix, K is the spring constant, so stiffness, and U becomes the displacement vector, and F becomes the load vector. This terminology, many packages, they use they use this terminology throughout. Even if you are solving the thermal problem, they will say that it is stiffness matrix, and this right hand side they will say it is load vector, and this they will say that it is displacement vector or something, although it may be temperature, but like terminology. Of course, my guide, Professor PM Dixit, he doesn't write this term, so he always is very meticulous in telling that this is the coefficient matrix, it is the right side vector, and this is that, you know, that nodal vector, okay, like that. So, but the thing is that terminology in the packages is like this. So this is how the stiffness matrix you get. Now the third step, once you have got this type of equation, so I just derived one equation for a typical element. Same thing can be done for all the elements. Instead of Ij, you keep on putting the different values, and you do that type of things. So you have to do now assembly in step 3. So for our 3-element problem, 3 elemental equations are what? They are AE by H, 1 minus 1 minus 1, U1, U2, minus F1, F2. For the other, it is AE by H, 1 minus 1 minus 1, U2, U3, minus F2, F3. And for the third one, I have written like this. Now, what you have to do, add these two together, these 3 of them. So how you can do addition? Addition of a matrix has been taught, but in this case, it is U1, U2, so it is very difficult for me to add. But so what I can do, that all equations, elemental equations, I write in a general global form. I know globally there are 4 nodes, U1, U2, U3, U4. So I just write in this one so that it becomes uniform. U1, U2, U3, U4. So what is the technique? I just put 1 minus 1 minus 1, 0, 0, 0. So many things have become 0, 0, 0. And similarly, I say that AE by H, then this become U1, U2, U3. So here U2, U3, this portion becomes non-zero. And the top first row is completely 0, last is 0. And when I write the third equation, then I say AE by H, 0, 0, 0, 0, 0, 0, 0, 0, 1 minus 1 minus 1. And I say that U1, U2, U3, U4 is equal to 0, 0, minus F3, F4. So I can do like that. So what I have done, these are the same elemental equation, no difference between the top row and between another this row. These are exactly the same equation, The first row we can call that these are elemental equations written in the local form, and these are the equations written in the global form. So in the global form, this is first elemental equation of the element 1, but expressed in global form. It is equation of element 2, but expressed in the global form. It is equation of element 3, but expressed in the global form. That is what this one. So that's why here it was first row and second row only, but this fellow now has gone in the third row and this has gone fourth row, because globally its position was like that. Globally its position was like that. Like your director is sitting in any meeting, that you know that first seat, maybe the chairman seat, but when there is a meeting with the, you know, that Ministry of Education and all NIT directors are there, then he may sit in the seat number 5. So you will say that my directors, who is my all in all, his position is in number 5, and another director may sit in number 7. So that means global position. So locally they are globally, the global, he is maybe first employee of your institute, global local position is 1, but globally the number may be different, okay, whatever the hierarchy there. So similarly that you have these equations, but they are written in the global form. Now addition of these, so now what is the advantage? You can simply add, just like you add numbers. So this fellow comes common, U1, U2, U3, U4. So this column vector has come common, and then this will be this plus this plus this. So 3 matrix can be added, and you know that matrix addition is what? Add each and every number, you get the matrix addition. So 1 plus 0 plus 0 minus 1 plus 0. And similarly, I try to add this also. So 0 added with the minus F1. So minus F1. Here F2, but in the other one it was minus F2. So automatically it got cancelled. It became 0. It became 0. In the last one, we had here F4. So this is F4. So that means this is what assembly has been done. Assembly, it is the assembly procedure. I have taught you in a very, very simple way that it is simply this is the assembly. But later on, when you study the course, you will not do the assembly this way. Not that in the paper there are some efficient techniques, because what we are doing, although very easy to understand, that is why that even the class 10 student can understand. That's why I have to explain in this way. But we are doing an efficient thing, of course. We are unnecessarily writing 0, 0. What is the need to write this one? Just make that something and keep putting those things. So for that purpose, we study some connectivity matrix and all those type of things. So I will not go into detail about that. If you come across that connectivity matrix, remember my thing that connectivity matrix is very useful in assembly. Okay, that is connectivity matrix. But unfortunate thing is that many of our students who don't have foundation strong, they think that okay, assembly is done using connectivity, and they just get bogged down with lot of terms. So I just want to assure that if you forget that type of things in a very lengthy way, you can do this type of assembly. Actually, you are doing this one in a lengthy way. So I am teaching in a lengthy way that what is FEM, that long way, so that you don't get any confusion. Okay. So if you can do anything in a lengthy way, sometimes I say to the students that when they face difficulty and they said that, sir, I am not getting the answer, and they show me 8,000 line program and they ask me to do that debugging. They said, sir, I am not getting it, is something happening this one, and my answer is coming very absurd. So I said that, can you solve that a simple problem by calculator? Okay, manually, then you will get the idea about that. So similarly, that if you understand basic concept, that whatever be the complicated thing, actually you are doing nothing but writing the elemental equation in this form and adding, doing the matrix addition. So now you have to put the application of boundary condition. So for the present problem, suppose you have U1 equal to 0 and F4 is equal to P. So what you do that? Boundary condition is F4 is equal to P. Unless you put the boundary condition, you cannot solve that also. Why? Because you see that F1 and F4 is unknown. So how should I find out U1, U2, U3, U4? Moreover, if you try to invert it, you will see that it is a singular matrix. So if boundary condition was that a load was applied at the end, so just put F4 is equal to P. That becomes very easy. Just put F4 is equal to P. And then what do we do here? What do we do here? Put F1 is equal to 0. I have written this equation. This is the mistake many people do that. I don't know that whether it is a so simple thing. Sometimes simple thing becomes very difficult to explain. Complicated things people understand very easily. But the people will, so this part you pay attention, it is very simple, but 90% students do not understand, and with very difficulty, I spend half an hour, then they get idea. Second boundary condition when I applied, don't think that if I have made F1 is equal to 0, I have written like this. No, I have not. I just saw that there is a boundary condition U1 is equal to 0. So what I did, okay, I have got U1 equal to 0. That means I have got one extra equation. It is, for me, it is U1 plus 0 U2 plus 0 U3 plus 0 U4 equal to 0. That means I have got one equation whose coefficients are 1, 0, 0, 0. So I say that 1, 0, 0, let us put that equation, and this is, and AE by H, if it is multiplied, then also it will be valid. So I am multiplying AE by H also here, no problem. Otherwise AE by H would have been inside. So I just wrote, so first equation is what? That is the your essential boundary condition itself. Okay, that is itself I am writing, and I am writing the 4 equations. I got one extra, and this equation, fifth equation, which was creating problem to me, that in which minus F1 was there, I just have thrown it out. Just I did not consider it. But I am silent about that. I am not telling that F1 is equal to 0. Unfortunately, because students do not pay attention, and unfortunate thing is that they only solve the problems mathematics, okay, this formula, that one. They will not understand even this simple thing that, you know, this is the thing. They say, okay, that F1 is made 0. F1 is not made 0. How it can be 0? F1 is F4 is equal to P. So in fact, I know also that F1 will also be P. So where it has, so then they say, no, sir, then where it has gone? It is 0 here, that you have written 0. Hey, Baba, because you do not know that how to convert simultaneous equation in the matrix form. That is why you are asking this question. I am not telling that equation. I needed to write a 4 by 4 matrix. I said that when there is extra equation, why should I take this difficult equation? I should take easy equation, and I have put that because for finding out all unknowns, I need only 4 equations. Now I have got 5 equations because U1 is equal to 0. So put it there. Had it been somebody might not have given me boundary condition also. Somebody just a ghuma ke problem de diya. If I twist it, then students will not be those who learn by rote. I say that I am not having any boundary condition. I know U1 is equal to not 0, but I know U2 is equal to 1. Now solve the problem. Now apply the boundary condition. I said U2 is equal to 1 here. Now up to problem mein aa gaya that U2 is equal to 1, and this is here it is F1. But if one who understands the basic concept, it is child's work here. What is the U2 is equal to 1? So first equation will be 0, 1, 0, 0. You at U2 place it will become 1, and that right hand side also it is 1 because U2 is equal to 1. So that is what this way we apply the boundary condition. Okay, correct? And then so once you have applied this boundary condition, now you can see that this matrix can be inverted, and you can find out the solution, and the solution has become U1 is equal to 0, U2 is equal to this much. It has, by solving this thing, you can solve this yourself, you can do inversion, you will get this solution, and we know that this is correct also. In that proportion it has come. So now once we have got the solution, then we may do post-processing many ways. I can plot a graph of this, that is also post-processing. But I am telling, let us say that we want to find out the strains and stresses. So in this example, strain in element 2 is equal to U3 minus U2 by H. and this is U3 minus U2 by L by 3. So P by AE, and stress is given by AE into epsilon, that means PA. So based on that, I find out the strain and stress and this one. So in this, up to this, if you have got any question, okay, is it okay? Otherwise, I can move ahead. But if you have got any question up to this stage, you can ask. Yes. Any question? Manojji, is there any question? We want to ask, or should I move ahead?
Yeah, please sir, move ahead, sir.
Move ahead. Okay, they have understood. Okay, nobody.
Yeah, understood, sir. Understood. Sir.
Are they listening, or it is only in the, they have kept in this one mute? Okay, means that is also the, we have out of that. Okay, so is it?
It is similar.
Huh?
It is similar.
Okay. So now, is it okay?
Yes, sir. Yes, sir. This is fine, sir.
Okay, okay.
Yeah, this is fine, sir.
Yeah. Okay, fine. Now, so we come to post processing, and let us say that here. Let us say that just give you one more example. Modal analysis will be solving the beam problem also. Suppose we have this type of beam, fixed beam with a central node. So what do we do that? Here also we can do pre-processing. I have taken 2 elements just to make it easy. I have taken only 2 elements, first element, then second element. And at the middle, at point 2, location 2, I have put a load, it is already a force P there. So it is better to take a node point where the force is there. So I just have taken it like this. Now if I take the typical element, this is E, and in this one, I and J are the node. So typically that in beam problem, you have deflection as well as the slope. So Vi and theta I. And here also you have deflection and slope, and you have force, vertical force we are considering, and moment. So only thing, the problem has become 1 degree higher. Earlier I was solving 1D problem, but otherwise there is no difficulty. So elemental equation, like in the previous case, we can get the elemental equation in this form. K1, K2, these are the coefficient, and this is Vi theta I, Vj theta j, and Fi mi, Fj mj. That means forces and moments, shear force and bending moment, they depend on the deflection and slope. But how do I find out that? I still can apply the strength of materials approach, and we say that, okay, suppose there is a force Fi acting and bending moment Mi is acting. So this is Fi h cube by 3ei minus Mi h square by 2ei is equal to Vi. And similarly for this one we have written, I am not going into details about that. Those who want to revise the strength of material, they should ensure that this is correct. That means suppose Vj is fixed and you are considering the deflection of Vi, and these are the forces, answer will be like that. So you will get these 4 type of equations. Those 4 equations you can write in the matrix form, so you will get a coefficient, and then you can find out that what are the coefficient, and these coefficients will be happening. Okay, this is written in terms of Vi and this one, but you have to do inversion, etc. You have to bring this side to this side, and then you will get these equations. So your elemental stiffness matrix will become like this. This is a elemental stiffness matrix for a beam problem, and you have. So now we should do assembly. So suppose in the same way, we write elemental equations in global coordinate system. So we just write this one, and this is V1 theta 1, V2 theta 2, V3 theta 2, 3. So you see in the first element only V1 theta 1, V2 theta 2 will come. Third node is in fact in the second element. So lot of zeros will come. Similarly about the forces, this is F1, M1, F2, element 1, M2, element 1. And for the second one is stiffness equation, I write like this. So this is 0, 0, F2, M2, F3, M3. And you adding this system of equation, if you add these, then you get what? That this is, you did simply addition, you took it common, and this part it becomes F1, M1 as it is, because 0, 0. But F21 plus F22 together, this will give the total force P, because you have applied in this case P, and M11 because there is no applied moment, so this is 0, and you will get F3, M3. So you have got basically this one, this type of equation, but you have got these 4 unknown quantities, F1, M1, F3, M3 is not known. So how do you to resolve this? You have to solve, you have to put boundary conditions. So applying the boundary condition, V1 is equal to theta 1, V3 is equal to theta 3 is equal to 0. That means it is fixed at both ends. So slope and deflection are 0. So what I can do, that in the same way, first equation is V1 is equal to 0. So I can say 1, 0, 0, 0, and this is 0. Second one is theta 1, 0. So 0, 1, 0, 0, 0. And then similarly, I can do for here. Here V3 was 0. So I can say 0, 0, 0, and then 1, 0, and this is 0. And last one is 0, 0, 0, 1, 0. So I will still have basically 6 by 6 equation, but a lot of zeros and this one. And that's what that I did in the previous problem. But you know that day by day we have to become smarter. That means that was the correct thing. Whatever you studied in class 1, that is correct. Class 2 also your teachers have made correct. They have not taught wrong. But only thing that you have grown up, so now you do the things in a slightly different way. So whatever I told, that was the basic thing that you should have been doing that. Again 6 by 6, but I got little smarter. So I said, okay, instead of doing like that 1, 0, 0, I already know that V1 is equal to 0 and this is equal to 0. Only V2 theta 2 is unknown. So why don't I just retain only 2 equations in which V2 theta 2 is there? Other things I discard. So I did that type of thing. That is, say V1 equal to 0. So you can do away with this row and this column. Similarly, theta 1 is 0. So you can do away with this row and this column, and then you can get system reduces to this thing. So it becomes very simple. It becomes 2 by 2, 1, and you can always get the solution, and your solution is coming nicely that V2 is equal to PH cube by 24 EI. Put P is equal to L by 2 by 24 EI is equal to PL cube by 192 EI. And theta 2 comes out to be 0. If you would have done by strength of material approach also, you would also get the same answer, PL cube by 192 EI. So why you are getting exact solutions here? Because here we are solving the simple problems. Actual deflection is cubic, and we are also assuming cubic. Because 4 things we are taking now, 2 deflection, 2 slope. So cubic function fitting is going on inside. So therefore everything is okay. But in the other cases, it will be approximate only. So I have shown this one. So this is also important. Now you have understood that general procedure of that, and I use the strength of materials, etc. But who is going to use this type of equation each and every time? So mathematicians have developed good methods. That one method is called Galerkin FEM. So what we do that in Galerkin FEM, that basically that we do that this type of thing. Let me just tell that with example only. Okay, you will understand what is Galerkin FEM. Now for solving a problem by Galerkin FEM, let us say I want to do it for axial rod problem, okay, longitudinal deformation of a rod. So I am just putting that Q function here, okay. Q is the load per unit length, okay, that means Newton per meter. If I have concentrated load like in the previous case, concentrated force can also be written in the form of Q using a Dirac delta function. That technique, you know that, okay. Otherwise, you have to do that in a complicated way. So basically, you generate a differential equation. Differential equation of a problem is given d by dx Ea du by dx plus q is equal to 0. Note that this is the differential equation actually. Q may be function of x. Q may be a concentrated force also, it may be something in between, but then we have to use that concentrated force multiplied by Dirac delta function, okay. So I will not go into that. Then you put the boundary condition at x is equal to 0, u equal to 0, x is equal to L, du by dx equal to 0. We have that type of thing. Then, so what do we do that? After we have got this differential equation, it is a second order differential equation, very strong second. So we want to weaken it. We want to make weak. That means reduce the order. So how do we say that we obtain the weak form? How do we say that? Suppose we say ye be the approximate solution of u for an element e whose end coordinates are xc and xc plus 1. So we say d by dx ea dy e by dx plus q is equal to r. So it becomes residual. Okay. Why it becomes residual? Because if y is the exact solution, then of course it will satisfy. But if it is not satisfying, it will give me some error that I am calling residual. Now my point is that I have to minimize the residual, or I have to make it 0. But it is very difficult to make 0 at each and every point. So I am trying to make 0 to vanish in some average sense. That means, okay, I am telling that suppose I take a weighted average. That means I multiply that residual by w and then I integrate dx. Then at least it must be 0. Right? So I am doing that type of thing. The question is that what you said that actually it has to be made 0. If it is 0, then it is automatically satisfied. But if it is this one, then at least this one, it should be multiplied with by w. Now, if w is totally arbitrary, that means w is anything under the earth, then this will be equation will be 0. That you can see. That means this is the lemma, that if you think. But you know that if it is not that, then it is approximate, because for some w it may be 0, but some w will be non-zero also. So you may get, your doubt is very reasonable. Actually, you are not face to face, so I cannot ask and I cannot interact. But you may be getting doubt that that what he is telling, that just multiplied by w. So I said, okay, w may be anything, then it is okay. But you know, w can be somebody choice. So I agree that it is approximate. Okay, some cases it will be like this. So that means, but we should try to take w as general as possible. But before that, suppose we have got this expression. So here w is a known some function, and which is without any differentiation, and ya is approximating function in which you are having double derivative. So how don't you do social justice? What you do that? You make both as a first order this one. So how should we do that? Because then continuity requirement will also be reduced. So integrate by parts. If you integrate by part, then you get this type of expression plus WEA dy by this one, and this is equal to 0. And this one, so this will be called weak form, because this is the weak form of the same problem. It is only first order derivatives are there. So since it is first order, I can choose the linear type of function. So we can say w is equal to w1, w2, n1, n2. n1, n2 can be coefficients. These are basically called the shape functions, and they are weighted. So how do we see that? Okay, so we see the weak form, and we say the highest order derivative is 1. So that means linear function is enough, and continuity requirement is the highest order of derivative minus 1. So we say C0 continuous. So a suitable linear approximation for the element can be something y is equal to n1, n2, and where n1 and n2 are Lagrangian type of shape function, this can be like this. So this is just Lagrange interpolation. You might have studied Lagrange interpolation. So we just have expressed like this. And once we have known that approximation, then in the weak form I can do also, I can differentiate ye with respect to x. I can get n1 prime and 2 prime. So I get this type of thing, and I automatically got the differential equation, and this is what the elemental equation. That's how we do that. So now the problem is that now my w1, w2, which I have kept there, that will vanish from all sides, and that was arbitrary in the sense that as the linear approximation is there, then these weights are arbitrary. That means this will hold good for any weights. But of course, it may not hold good for quadratic. But since your assumption is that in a small domain, everything is linear only, so it will give fairly approximate result actually. So that is what we do, and we get the same type of stiffness equation. You get a load vector, plus you are getting some extra term, you are getting internal load vector. These will cancel with each other when you do assembly. Okay, that's what it comes. And so that is one approach. This is called Galerkin FEM. In the rich FEM, which is called variational approach, that you go from the opposite side. There you don't need a differential equation. You have to start from energy. So any differential equation can be converted into integral form also. So what is that? Suppose beam problem. If I want to solve the beam problem, you have to do the differential equation of the beam, but we can do it by writing the potential energy of the typical beam element. I have written the potential energy, and then minimize the potential energy that gives the solution. So here also, here you don't have to make weak form because it is already weaker form. So here completeness you same way, highest order, continuity is highest order of derivative inside the integral is 2. So C1 continuous, and you take this type of shape functions, element approximation. Actually, you will take a plus bx plus cx square plus dx cube, and then by deriving, putting the nodal values, you will get this type of expression. And then you put it that and say minimize potential energy with respect to elemental equations, and you will be getting this type of things. So what happens that you get this one. So this is rich approach. So the same type of approach you can actually extend to plane stress and plane strain problem, like basic equations are this one. Say in plane stress problem, you get these two equations: force divergence in x direction, force divergence in this other direction. These are called the momentum equations, and you may have boundary conditions at various places, but procedure is basically same. You have to obtain the weak form of these equations, both the two equations, and do that type of thing. Manojji, I have some time, or it is this one? How much time?
Yes, sir, you can continue, sir. 15 minutes. 15 minutes, sir.
15 minutes I can continue. Okay, fine.
Yes.
Okay, right. So then what happens that this is this one. So it is now stress and strain are related by the constitutive matrix. So you have to take a constitutive matrix. Everything in a FEM, if you want to write coding, etc., you have to be strong in writing the equations in the matrix form. I am telling one thing, because you know it is basically what I have written. It is nothing, anything big thing. It is the same equation, you know, generalized Hooke's law, epsilon x is equal to 1 by E sigma x, but whole thing I am writing in the matrix form. So these are called the elasticity constant. This is a strain displacement relation. Epsilon x is equal to del u by del x, epsilon y is equal to this much, and 2 epsilon x y is equal to this much. So then you can solve this problem of 2D in this one also, potential energy way also. You write the total potential energy in terms of the stress strain, as the thickness is independent of x and y. You can write this equation, potential energy. Then you write that whole thing in the matrix form. Even the product sigma x into epsilon x, sigma y, epsilon y, this much big expression in which three things are three terms are added. I am writing it like this. This row vector of strain and multiplied by this dot product becomes this. So that's how that I am doing that. Everything I am writing. Then you are developing the equation becomes easy. Then you put the finite element interpolation approximation ui ni, but that also you write in the matrix form. N1 in Nn, and this is this one, it is equal to this one. Then put that thing, everything in the matrix form, and you becomes like this. Epsilon E becomes like this, sigma E becomes like this, and just substitute it there, and then you differentiate with respect to delta E, that means modal vector. So just like you do differentiation with a scalar quantity, you can differentiate at one go with the vector also. So those things you should be familiar, that suppose you differentiate in this one, it is delta E transpose delta E. So you differentiate it with delta E. So two terms will also come because it is square type of things. But here it is only one delta ET, so it will not come the square type of thing. So these type of things also you have to be very familiar. And this, so after doing that, automatically you will get this equation, and this will be called the stiffness matrix. This will be load vector, and this is internal load vector, like that. So procedure is very simple. Now the element can be any type. You can have in 2D, you can have whole loaded element, and you can have interposition function like this. You can use the natural coordinates, xi eta, instead of the physical coordinate. All these type of things you will be studying in the finite element. That's why it becomes one semester course. Otherwise, basically, it is essentially what I have told in one lecture. That is enough to understand finite element. But you know that you will do that. Not only that, the 2-3 lectures will be on this topic also. That okay, Dixit sir has told that how to find out the stiffness matrix and other things, but how to integrate and something. So your teacher will teach that one course on Gauss quadrature, that 2-3 lectures. About that integration can also be done numerically using Simpson rule, but Simpson rule is not that good. In fact, Gauss quadrature works better. So we teach that also. We teach that Gauss quadrature and this one, and then we apply the assembly of elemental matrices, and that is done in your package. It is done automatically. Otherwise, procedure is same as I have told. Then put the boundary condition. We have essential or geometric boundary condition like displacement got prescribed, and natural boundary conditions like your traction vectors got prescribed. Okay, so this type of thing, you put that boundary conditions, and then after that you do the solution, and then this much you have to do. This is finite element. But in the package, just I have to make the diagram and say that this is the suppose plate with a whole problem I have to solve. So I can be little clever also. I say that it is symmetric. So why don't I cut into 4 parts and just analyze one part? So I can do that one part, and boundary condition I have to carefully understand. Because of symmetry, it will neither go up nor come down. It is equal to both sides, up and down. So that's why V is equal to 0, and here U is equal to 0, because it will go neither this way nor that way, and load is applied here. This is a traction-free surface, no stress is there. And we solve, just put that boundary condition, then you know that ANSYS, automatically will do the solution, and these will be the stresses, and we can see the contour, that red zone. Here the stresses are very high. Here I applied 100 megapascal, because it is almost 100, 199, 90. But here you are getting about 335. That means about 3.3 times increase in this one. You are observing that is stress. Okay, so this is what that that I have told, and I think that the rest of the things I'll leave for discussion, and this is the way FEM works. I think in the introductory lecture, assuming that many of you may not be knowing FEM, and those who know also, they can find the other perspective I have presented. And now I will stop presenting. Any question is there, then I can ask, or any comment, I welcome. Yes.
Dear participants, if you have any question, please ask. Dear participants, please ask question, please. Dear participants.
Good morning, sir. This is Sanjay Kumar, PhD scholar from NIT Jalandhar at the Department of Mechanical Engineering.
Yes.
Sir, please suggest the tool for the FEM, which is the best one, and how and why we can choose that best FEM software for the particular solution of any complex FEM problem.
Okay. Yeah. Yes, of course, that it is a good question, because there are many packages and you want to know that what is the best one. So it becomes somewhat difficult to tell, because there is no one answer. But let me tell that as far as solving number of linear problems, elasticity problem, ANSYS is quite widely used. I can only state that it has become more popular. ANSYS Fluent Combine also. So another thing is that, but it was not that effective in solving non-linear problem. So nowadays, those people who are working in analysis of metal forming, etc., they are using abacus. Abacus, you have got this one. So these packages, and you have freedom to write. In fact, in ANSYS also, you can write some subroutine here also, in abacus also. And then there are other packages for different problems. Electronics people, sometimes they prefer Dyna, Make, these type of things. But as far as mechanical engineering is concerned, mostly the ANSYS and abacus are very popular. There are other packages also like Nastran and this one. Anything can be used. You can learn and you can understand. So what I can tell you one thing, even Cosmos also, some people from Cosmos came, they said my package is also very cheaper, and NISA was also there. So what I am telling that, and then there are open software packages also for geotechnical areas, etc. There are some open FEM packages. So there are plenty of, but if you want to know that naturally, if you want to just get my expert, this one, so since I have been using that, so I would say that ANSYS and abacus. Other than that, suppose somebody is doing metal forming problem, he can directly use deform package also. But in the deform, your job even gets simple because they have written, they are like further, that cooked thing. See, in this one, ANSYS and abacus, at least you have to do some job. But in deform, you may not have to do even that job. There you have to say machining, so machining module you have to pick up. Okay. So, so advantage is that the things will be very faster. But the disadvantage is that you may not have that much freedom as you have abacus, etc. So it depends that what is your application. Suppose you are doing mostly experimental work and you have done some metal forming problem, and suppose you want to say that, sir, I have done forging problem. What package I should use? I can say deform, or I can say forge 2D or forge 3D is also there. Both packages, because they will give answer immediately. And you don't have to do deep research in FEM. You just have to validate one. But if you want to say that, no, I will develop my own process or something, then it is abacus. But if you say that I want to do simple vibration analysis, modal analysis, then maybe ANSYS is more popular. So this question will be decided on that if you know one package very well, to pick up the other package, it will take only 5-10 minutes, okay? Means for very smart guy. And for a mediocre guy, maybe 5-10. If you are very weak, maybe 5-10 days. Otherwise, there is no this one. But generally, if you go to most of industries, what package is being used, that we try to learn. So therefore, we mostly concentrate on ANSYS and abacus. These two packages have become internationally very popular. So we focus on that, right? So this is like AutoCAD. Na? So you say AutoCAD, but we cannot say that AutoCAD is a solid edge vehicle. Okay, that is also good. But AutoCAD, because since AutoCAD everybody knows, or even now KTI is also becoming popular like that. Okay, so Sanjay, I think I have answered your question. Is it not?
Thank you, sir. Thank you very much, sir.
Yes.
Sir, I have one question also.
Yes.
Sir, I am Shekhar Shrivastava, Industrial and Production Engineering Department, NITJ.
Yes.
Sir, I have one question. As you were discussing about Galerkin FEM and Ridge FEM.
Yes.
So suppose we have a multi-physics environment in which we have coupling. Suppose the example is thermal structural problem. Mm-hmm. So in a thermal problem, suppose I am choosing Galerkin approach, and in structural problem, if I am going with Ridge approach or vice versa, will it be feasible?
Yes, why not? It can be feasible, because if you are there also these problems, a coupled problem can be also solved in this way. One is the sequentially coupled problem, that you solve that first the elastic part, then go to thermal, again you take the data of thermal, then go solve elastic again, and again you do that back and forth one. Other is the combined one. So if you want to follow the combined approach, then naturally you should have combined differential equation, or you should have combined energy expression. So the question is that then you have to follow only one approach. But if you want to do in the decoupled way, then you can follow that approach. That means this one. So it depends that if you have differential equation in whatever form, that way you have to move. Okay. Yeah.
Sir, you mean to say that in coupled solving, we have to follow one approach?
Because see, suppose somebody has given you differential equation only, in which that means my stress equation is containing some temperature term and heat conduction equation is containing some stress term. You know that many even heat transfer people may not be knowing also that in heat conduction equation also there will come some terms of stress and strain actually. That we, because this is advanced topic, so many people don't study that. So naturally that this will be this type of thing will be there. So if you don't have energy expression, then how you can solve that? My question is like that, because you have differential equation only, and if you have only differential equations, then Gazelkin can be used. Using the Lich method, you need the variational form. That means you need the energy expression type of thing.
Okay, sir, one more question, please.
Yeah.
Sir, I want your comment on the the amount of error we have between FEM results and its experimental validation. How much percentage variation is acceptable?
Okay. So this is error analysis is one interesting topic. Yes, but error, I would tell that how much will be acceptable, that becomes from the physics of the problem. Generally that we people in engineering, we used to say that 5-10% error was acceptable between physical, because if you are talking about that how much difference will be with the experiment and your FEM model, then the question comes that what was the accuracy of your input data and all those type of things also, because this is dependent on the physics. But the question is that how much error is there between the exact solution of the problem and your approximate FEM solution. That becomes the error analysis, because that nobody has control over that what will be the physical parameter. Suppose Young's modulus of elasticity is 200, I am putting in my FEM, but actual was 250, then naturally there will be huge error. So that question is actually related to overall engineering judgment. So that I am telling that usually 5 to 10%, but really it depends from problem to problem. Okay. But the second part, that how much is this one, that it is a big question. In fact, area is still open for this type of things if somebody wants to do research. That I gave that some solution by FEM. How do I know that this is accurate actually? So usually we do this type of procedure. I took that, say, something 100 element, I got this, and when I took 400 element, I get another answer. But there is a difference is very less. So I say that it has got converged, right? So what happens that this I am saying like this, but the thing is that in many cases, but even then, how do you know that it is close to reality? So for that, error analysis is done. And there are many techniques, that is a different topic, which I have not covered here. It is covered in one chapter of my book also, and it is a separate discussion. Okay, thank you.
Okay, so thank you, sir. Thank you.
Yes. So, so I think that Bagaji, there are no other questions, I think.
I think, sir, one participant want to ask question. I forgot his name. One participant is interested to ask you one.
Dr. Vishal Sharma, I am seeing Vishal Sharma. He wants to ask question?
No, sir.
Thank you, sir. No, sir. No question.
Okay. He will ask only one question, sir, when you are coming to Jalandhar.
I think Vishal sir is in Jalandhar. Am I right, sir?
Yes. He's
yes.
in Jalandhar, yes. Okay. So I think it's okay, and then they can, if anybody gives any email, you can forward to me actually.
Right. The question I will forward to you.
Okay, fine. Yes.
Yeah.
Okay.
If no question, then I thanks to Professor Dixit sir for wonderful introduction of FEM on this course. Thank you, sir. Thank you.
Thank you very much. Thank you.
Thank you very much, sir. Thank you, sir.
Okay, sir. Okay. Yeah, dear participants. Yeah, we will meet at 2:30. Okay, we will meet at 2:30. Okay, now you can leave. We will meet at 2:30.